Dear students, in this lab, we will study about synthesis of periodic signals. This is lab 6. So in preparing to this lab, you need to read about Fourier series representation of periodic signals. We already studied in chapter 3, but you have to review this. And the Lab 6 report, a submission near to both the theoretical work on Fourier analysis and the MATLAB simulation codes, results, including figures, and discussion of the theoretical and the simulation results, the MATLAB results. You have to compare both, and you need to give discussions. The purpose of this lab is to study in MATLAB how a periodic signal is reconstructed from its components or from Fourier series coefficients, and how the number of the components determine the accuracy of the reconstructed signal. If we start the basic theory, as you know, if I have a periodic signal x of t, it is represented using Fourier series synthesis equation. Using this, x of t is equal to summation of from k minus infinity to infinity ak e to the power of jk omega naught t, where omega naught is 2 pi over the fundamental period t. Now, this is called the synthesis equation because we are going from frequency domain to time domain, and we are building the signal x of t from its Fourier series coefficients. The AKs are, in general, they are complex numbers, or they can be purely real numbers also, depending on the type of signal. So in case if they are, of course, complex numbers, they will have magnitude and phase. Now, how we find this AKs? The AKs can be found from the synthesis equation AK 1 over the period integration of over 1 period x of t multiplied by e to the power of jk omega naught t dt. So we need to select one period and integrate over one period the product of x of t and e to the power of jk omega naught t. One period can be, for example, from t over 2 to minus t over 2, or from 0 to t. So we can select a convenient integration interval to get the AKs. Now, in this lab, we will see how the reconstructed signal x of t is affected by the number of components. Theoretically, the formula says from minus infinity to infinity. However, when we try to implement it in a computer, we have finite sum. So how we build the signal using the finite sum, of course, we will have from k minus k max, a certain number k max, to k max. By selecting k max, we can increase the accuracy of the reconstructed signal x of t. That means, for example, if I have k max, for example, 10, it will become summation from minus 10 to 10 ak e raised to jk omega naught t. So we will build the signal by using this k max. But if we choose another k max, for example, a bigger number, k max 50, then it will be the summation from k is equal to minus 50 to 50 ak e raised to jk omega naught t. So if we see the reconstructed signal for k max is equal to 10 and k max is equal to 50, it is clear that the result for k max is equal to 50 will be more accurate, close to the theoretical result for x of t. So in this exercise, we take in the first exercise, for example, we take here a periodic signal, a square pulse signal. As you see, this is a square pulse signal, which is equal to 1 from minus t1 to t1, and 0 from t1 until this point. This point is t minus t1, and then it repeats, this pulse repeating itself. Okay, this is a square pulse signal, periodic square pulse signal. It repeats every period t. And for this, what you should do, first of all, you need to find the theoretical values of the AKs. The AKs as a function of K, capital T, and T1. This will be a paperwork. Okay, first you have to calculate by using the analysis equation here. So by integrating over one period, for example, you can choose from minus T over 2 to T over 2. And you'll find AK as a function of K, capital T, and T1. And for B, you'll substitute capital T is equal to 4 times T1. And after that, you'll get a purely a K-dependent AKs. So the AKs will be a function of K. So this will be the theoretical part. Okay, for the MATLAB part, after we found the theoretical results of the AKs from the theoretical calculation, we will plot them as a function of K for different values of K max. For example, K max 10, K max 50, K max 100, and so on. And we need to plot the magnitude and phase of the AKs. The magnitude using subplot command. So the first row will be, for example, the magnitude of AK as a function of K, and the second row will be the phase of AK as a function of K. And very easy in MATLAB, we have the abs function, which gives the magnitude, and the angle function, which gives the phase. And you can make also axis labels, X label, Y label, and you can have axis range from minus K max to K max, from minus 4 to 4, the Y axis, for the X axis from minus K max to K max, and you can plot them. So you have to do for K max 10, 50, and 100. Here I give you a start, some example for the program. So what you have to do is just substitute the AKs that you found. Here you see, I have, for example, for K max 100, I have this, I defined K max 100, and then K is from minus K max to K max in steps of 1. So in steps of 1, because K is integer. So you need to find AK, and then you need to find AK K max plus 1. What is AK K max plus 1? Actually, this is the center point, because MATLAB indexes start from 1. So the AK K max at K max plus 1 means A0 for our case, the DC component actually from the Fourier series analysis equation. So if I use the AKs that I found from the calculation, I may encounter 0 over 0, so undefined. So for that case, that's why here from the theoretical result you will find A0, and that value will be AK at K max plus 1, which will be A0 here. Then you use subplot command. For the first row will be the magnitude, and the second row will be the phase. Very easy. For example, I can show you here in MATLAB. I have, okay, this is a calculation after I got. You can do it by yourself. By the way, this signal is already in the textbook, so please refer in the textbook the calculation for the AKs. So here I defined K max 10, and for K from minus K max to K max. Here 2 dots means if you do this, that means the step for K will be 1. Okay, so in steps of 1. And then I defined AKs. AKs are given by this. And then AK max plus 1 half, which is 0.5, which is this value is A0. In fact, it is A0. And then I use here the first row of the plot, subplot 211. When I say subplot 211, means 2 rows in 1 column. And in the first row, then I put the magnitudes. The magnitude I use here to plot steam K absolute values of AK, and then the axis from minus Kmax to Kmax from 0 to 0.6. This is x-axis, and this is a y-axis. And then I give x level, K, y level, the absolute value of AK. And in the second row, I plot here the phase also by calling the angle function. So let's see, here I saved it using CTFS1, which is, this is the script file, CTFS1. You see, this is the absolute value of AK versus K. The value at 0 is 1 over 2, and the value at 1 is this much. And of course, if you use data type here, you can know what is exactly the value here. The value at 1 is, for example, 0.3183. And here is the phase plot. The phase at 0 is 0. The phase at 1 is 0. The phase at 2 is at 1. At 2 is 0. And the phase at 3 is this one. For example, if I use here a data cursor, here another data type here, the phase at 3. The phase at 3 is pi. So these AKs are actually real numbers for this example, and sometimes positive, so they don't. The phase will be 0, and when it is negative, the phase will be pi. Okay, so this is for Kmax 10, and you will do for the other Kmax 50, 100, and so on. Very easy to follow this. Okay, now what about the second part? Actually, the third part. The first part is the theoretical, 2 is the MATLAB. In the third part, we will try to reconstruct the signal from its Fourier series coefficients, AKs. Basically, what we will do is we will use this formula. That means, so x of t summation of AK e raised to jk omega naught t from k is equal to minus k max to k max, because we can only have finite value for case when we are implementing in the computer. So then we vary again k max 10, k max 50, 100, and so on. And for this example, we have to use the period t. The fundamental period is 4 seconds. And we have a function called CTF synthesis. What does it do, this one? It will reconstruct the signal from the AKs. So I have this function. This function, I posted it in Blackboard, so you can get it from there. And you can use this function to reconstruct the signal. So you will make a small script file, and in that script file, you will call this function CTFS synthesis, and then you will reconstruct the signal x of t from the AKs, and then by varying k max, you will find different graphs, and you will be able to learn that when k max increases, we have better accuracy, or we are close to the theoretical result. So again, I started here some small program. I will show you here in MATLAB also. Okay, so here the first of all, what is this CTF S synthesis function? Let's go through this. So here what is this function? This function, this is the name of the function. So this is how you program functions. So this is a function name. These are the variables you will give as an input. For example, in this case, the period t naught and the a case. And then this is the output. The output will be the signal x and the time vector t. So by calling this function, I will get the signal x and the time vector t. That means. Now, if we see this function, what it has here, Kmax. What is Kmax? Is length of AK minus 1 over 2, because we are going from minus Kmax to Kmax. So length of AK minus 1 over 2 is Kmax. Then here the maximum frequency for the sampling frequency of the signal x of t is defined as Kmax times 1 over t naught. 1 over t naught is the period of the signal. And then here is the time steps. The time steps for the signal is from minus t naught to t naught, and this is the time vector. The time vector from minus t naught to t naught, and the time steps is 1 over 8 times maximum frequency, which we defined it here. We are sampling at 4 times the Nyquist rates, that means. And here omega naught 2 pi over t naught, of course, and k from minus kmax to kmax. And here is the exponential function. What is this exponential function? From the theory, the exponential function means, when I go back to the theory, this one, e to the power of jk omega naught. This. So this is the theory. So again, go to the MATLAB. So we define ek exponential of j t transpose times k times omega naught. K is here from minus kmax to kmax, a row vector, okay, and t is, it was a row vector, and we changed these to column. So it will be, it will have length of t. The size of t will be length of t times by 1. So it will be a column vector, length of t times by 1, and k will be length of k 1 times length of k row vector, 1 times length of k row vector. Then if we define ek like this, we'll get a matrix which is length of t by length of k, length of t by length of k. Then after that we get the signal x of t. The x of t is this matrix ek multiplied by ak. Ak is a column vector. So a column vector which is length of k by 1. So remember, ek is length of t by length of k, and ak is length of k by 1. So the result, after you finish, after when we do this calculation, this matrix multiplied by this vector will get length of t by 1. Okay, the signal x of t, which is length of x by 1. So this is what we get from this function, CTFS synthesis. So it will generate the signal x of t using the a case and the period. All right. Now let's see how, for example, I used this function to this script file. Okay, this script file, I am going to reconstruct the square pulse signal, the periodic square pulse that we saw from the theory part. So I define here t naught is 4, k max is 10, then k is from minus k max to k max. Then here I define the a case. The a case is that we found from the theory, sine k pi over 2 over k pi. Note that we should put dot here because it's element by element division. Then here AK max over 1, that means A0. A0 is 0.5. Then here I call the function CTFS synthesis function, because I define T naught here and I have AK already. Then by using T naught and AK, the output of the function will be X and T. So I get X and T, the signal X of T and the time vector. Then I can plot as a function of X of T as a function of time, and I can give axis level, X level, Y level, and axis interval also. So here I will plot it for the first time for K max 10, and we will see how it looks like. So my function is CTFS square 1. Okay, CTFS square 1. So let's be clear first. This clear. CTFS square 1. This is my function. See, this is the square pulse. How many periods? 2 periods. So I start from here, from -4, and then here 0, 1 period, and then another period from 0 to 4. Okay? So because it will generate, the CTFS function generate 2 periods, the synthesis function. Now this is for K max 10. So if I increase K max, as you see, there is some ringing here. Why? Because I have finite value of K's. Because originally we defined it from -infinity to infinity. However, here in the computer, when we try to implement, we used finite values of K. So that's why. So this is for K max 10. Let's do for K max 50. So I will change here. Only I change K max here. 50. And I will plot on the top of this. So I change this the color, for example, to blue. And then because I made some changes, so I have to update here, save. And I will plot it on the same plot. So I say hold on here, hold on. And then I call my script file. Okay, let's see now how does it look like. See, the blue color is K max 50. The red color is K max 10. Which one is better? Of course, it's obvious. K max 50 is more accurate, very close to the theoretical curve or graph for the square pulse. So by this way, we understand that as we increase the case, the number of cases, as we have more A case, then we will be more close to the accurate value of X of T. So you can do this exercise for the other values of K max. Okay, so that is the third part. In the fourth part, I have another signal which I defined the A case. AK is equal to 0 for K is equal to 0, for example. And for the other case, defined by this. So you need to make a script file, another script file, but you use the same function for reconstruction. For reconstruction, you use the CTFS synthesis function. But what changes you will make, you just define AK. So for example, here in the MATLAB, so for these two lines, you just change these two lines, AK and AK max plus 1. And you call the same function and you try to plot the graph. By the way, the axis level, you can remove it. Sometimes it may clip the graph because I forced it here. I made it from minus T naught to T naught, from minus 0.2 to 1.2. So you can, if you like, you can remove this. And first you have to try it by that way. For example, here I close this and I call the function again. See, then I have again the plot of square pulse. You see, this is for Kmax 50. So by it will use its own axis interval. So you can, if you put here a percentage sign, that means it will not execute this. So you can do that. So you have this A case here. For this A case, plot the graph for Kmax 5, 20, 50 using three different colors and on the same graph so that you can compare the difference. And you can use here axis label here. I already axis interval from -4 to 4, from -0.5 to 1.2. And in the fifth exercise, another signal. This will give you one type of signal, and here another type of signal. You will reconstruct it again by defining AK. Here, remember how is the AK defined? AK is -1 over 2k squared times pi squared, when k is odd number. Odd number means 1, 3, 5, -1, -3, and so on. Okay? And 0 otherwise. For the even numbers, that means 0, 2, 4, 6, 8, -2, -4, -6, and so on. So you have to define the AKs in your script file when k is odd and k is even, for example, here. And you use this formula to build your script file. And then you will use again the CTFS synthesis function and reconstruct the signal for Kmax 4, for Kmax 10, 20, 50, and you will use axis labels again, and axis interval from -1 to 1, from -0. This is the x-axis is from -1 to 1. The y-axis is from -0.15 to 0.15, and you will reconstruct the signal, and you compare the signal, the graph for the different case, Kmax 4, 10, 20, and 50. So that's all about lab 6, and you can get further theory in the textbook. Read about Fourier series to have more understanding how reconstruction is done from the A case. And I hope you understand this lecture. Thank you for listening, and see you in the next lab lecture.